Okay, so we will continue from the previous problem, that is there is another problem. It says that there is a vessel that has a displacement of so the displacement, there is a vessel with a displacement of 25,000 tons and it has a K. So, it's some hydrostatic data are given, kg equals 10.6 meter, it gives km equals 12 meter, kb equals 6.1 meter. So, this is the second type of problem where you have you are given your hydrostatic data and not you are not calculating your I or anything. Therefore, now you are also told that angle of deck edge immersion is 27 degrees. I will tell you what, I think I have said what it is, but the meaning of angle of deck edge immersion is that suppose you have a vessel like this. Okay. So, this is obviously your deck, you know that. So, this is your W 0 L 0. Now, if it heels at this phi, you know that this will be the deck edge, it will be immersed. So, this angle of phi is called the angle of deck edge immersion. So, it is the angle to which the ship should be heeled such that the edge of the deck will be immersed. So, as you can see from the figure, it is straightforward. So, that is a now you are told that the angle of deck edge immersion is 27 degrees. Now, the question is calculate the dynamic stability at 20 degrees heel. That means you are asked to find the dynamic stability up to 20 degrees. I guess that is what it means. Yes. So, you are asked to find the dynamic stability up to 20 degrees. Now, just as a word of caution, that is you will see that till your mid semester, in fact, whatever you have done is in fact simpler compared to what you are going to do after this. Okay. It is much simpler. There are lot of things after your after what you have done. So, the other one was just mostly you knew Archimedes principle, a little bit of GMBM and all that, little bit, but not much. It was much simpler, because after that we have done dynamic stability. Then even you will, if you remember the classes, you will see that the ones coming after that, like wind heeling arm, calculating the grains, those things are really very complicated. If you start doing the problems, you will, it's complicated means there are a lot of things you have to remember. First of all, the formula, all the load line regulations you have to remember very clearly, grain regulations you have to remember clearly, and that heel, how it is done, you have to know. If you remember the wind, I took one full class to do just the wind heeling arm. It was very confusing. You have to take some 1.5 lambda 0 1.5 lambda 0, you have to draw a line. If just I am just cautioning you, that is it's your end semester won't be that simple, okay, like your mid semester, it will be much more involved, because if I ask you problems, this problem itself you can see everything you have to know, what is dynamical stability, how to calculate dynamical stability, and when you go into grains, wind and all that, it becomes much more complicated. So, just be careful for the end semester. Okay. Then this problem says calculate the dynamic stability at 20 degrees heel. Okay. So, first of all, you have to calculate your GM 0. GM 0 is equal to Km minus Kg. This is straightforward. This you have to do. So, that will give you 12 minus 10.6, that is 1.4 meter. This is your GM 0. Then you have to calculate Bm, which is also Bm 0, which is equal to Km minus Kb. This is the second thing, which will give you 12 minus 6.1 equals 5.9. Okay. So, this is your now. So, the problem here is to find the dynamic stability. Of course, you have to know that dynamic stability is the area under the G z curve, that is the meaning of dynamic stability, not G z curve, delta into G z curve. Delta is the displacement of the ship. Okay. So, delta into G z, the area under that delta into G z curve is what is known as the dynamical stability. So, that means first of all you have to get your G z curve, okay, then only you can do your dynamical stability. So, in this problem even your G z curve is not given. So, you have to calculate the G z curve, that is the only additional thing in this. So, how do you calculate the G z curve? You use the wall sided formula. So, you have to make your G z table. In this case, you have to generate your G z table using the wall sided formula. G z is equal to sin phi into G m plus half B m tan square phi. Now, the usual way is you take 5-degree intervals, start from 5 degrees. In this case, you have to go up to 20. So, 5, 10, 15 and 20, you take 4 values and you make your G z table like this. Well, heel 0, 5, 10, 15 and 20. Then well, you just have to do this whole thing, half P m tan square phi plus G m into sin phi, that will give you your G z. So, that means you have to calculate that, do that calculation of G z using this formula here, and you will get your G z. Okay. All those values of G z you get. Then you get your have your Simpson's multiplier 1 4 2 4 1 and function of area, same thing, that is this 0 this I mean G z multiplied with the Simpson's multiplier comes here. Okay. Each of these G z's multiplied with the Simpson's multiplier uses the function of area, and once you have that, you have that your area is equal to h by 3 into sigma function of area. Therefore, this is equal to 1 by 3 5 by 57.3 into all these things 5 degrees. So, 5 by 57.3 radians into function of area, whatever it becomes, so many meter radians you will get. Okay. So, this gives you the dynamical this is the area, and dynamical stability will be this multiplied with the displacement. Dynamical stability will be whatever area you are getting here multiplied with W. So, that will give you whatever, it does not matter. So, this will give you your dynamic stability. Now, there are different possibilities here, means you are given problems in different types, where you are in finally the main thing will be to calculate, see if it is satisfying the load line regulations. Okay. So, once you remember the formula, so in these kind of problems, note that once it is not, as far as you are concerned, for the problems there are 3 types of regulations. One is for grains, one is for wind, and one is for general. Okay. So, remember this, there are going to be for problems wise, when you are asked any type of question like does it comply with the regulations, anything like that. So, 3 formulas you have to, 3 set of rules you have to remember. Why I am saying this now is because the next chapter or the next 2 chapters later, there are going to be a whole series of formulas. I will say talk about formulas adopted by the UK Navy, formulas adopted by the US Navy, adopted by German Navy, like that. Okay. Different formulas are going to come. As far as when you get a problem, I am not going to include those formulas, do not use those formulas, because problems will be just based on these formulas. So, for the problems part, there are 3 types of formulas required, or 3 types of load line regulations required. One is the load line regulations using grain. So, the moment you see grain anywhere in the problem, means in the it is a ship carrying grain, it is a container carrying grain, you see that word grain anywhere, you have to use those formulas, not anything else. Okay. Similarly, number 2 is wind. The moment you see that the problem is to do with wind, it says wind velocity is this, find the healing due to wind. Anything to do with wind, you have to have a set of formulas, that I mean set of regulations, that also I have told you already, it has been told. So, always use those formulas. If it is not either of these, anything else, any other kind of ship, whether it is fluid, anything that you are not used to, if it is fluid or water or ballast, they will say, or anything ore, no ore, probably better use grain. Then anything else you see, you use these formulas, that is the one I have said, that is the initial up to 30 degrees should be less than 0.055 meter radians, that one. Okay. So, there are 3 set of rules, remember that. Later all those things that I am going to discuss probably 2 weeks from now, those do not apply to problems. So, just remember that and keep that. Okay. So, this is okay, I think there is one more problem. Okay, this is also actually we haven't used that deck edge immersion anywhere, right, in this. Usually this deck edge it's no, in this problem that term was this, that 27 degrees was not used anywhere really, it is not used, I mean, but you have to use it. If you remember, in the wind derivation, when you are calculating the wind healing arm, and when you will be asked is this kind of wind is acting, or even if you are not told, you have to, suppose you are asked, see if the ship is stable as far as the wind is concerned. So, when you are asked a problem like that, it is to do with the healing arm due to wind, which I have done one full class, it was just that. So, in that, if you remember, one of the criterion was that one of the angles should be less than the angle of deck edge immersion, one criterion was that, one of the rules is that. Okay. So, remember that, that is why usually you have to this is given, deck edge immersion is usually given to check one of the criterions, that is one of the angles should be less than the deck edge angle, that is there is a use of that in this problem, but we are not using it anywhere. Okay. And okay, the next problem says there is a box shaped vessel, again it is a box shaped vessel, it has a length of 120 meter, it has a breadth of 18 meter, depth of 12 meter, and it is floating at a draft of 8 meter. So, you are told that it has a draft of 8 meter in fresh water, and it has a kg of 7.278 meter. Now, you are told that a weight of 432 tons. Now, what we are going to do is, you are going to load a weight 432 tons is loaded at kg equal to 12 meter. Okay. So, a weight of 432 tons is loaded at a kg of 12 meter. Now, the problem will be like this, most likely it will say that find the dynamical stability of the vessel up to the angle of deck edge immersion. Okay. That means two things, one, you have to first find the angle of deck edge immersion, and then you have to find the dynamical stability up to that angle. That means up to the angle of that deck edge immersion, you have to find the area under the delta into area under the GZ curve, that you have to find, that is the dynamical stability. Okay. Now, let this be here. So, this is the problem. Okay. Then first of all, let us find the displacement of the ship before the weight is added, or that is the initial displacement. So, initial displacement of the ship is equal to L into B into D into rho. that is equal to 120 into 18 into 8, 8 is the draft into 1, so many tons. This is the initial displacement of the ship, it comes to 17,280 tons. Okay, so this is the initial displacement of the ship before the weight is added. Now, then we need to find after the weight is added. So, weight added, then you have your this is enough. Weight added, then you have your kg, then you have your moment. So, the initial weight of the ship is 17,280 tons, and your kg, remember you are given your kg 7.278, and therefore, your moment you multiply 755.2 will come there. Then you are told that okay, thank you. Okay, then you are told that you are adding a weight, you are told that a weight of 432 tons is loaded. So, 432 tons is loaded. So, this is added, and you are told that your kg for that is 12 meter. So, 12 you multiply this, you get something. So, you find the total moment, sum this up, and so this will give you your total. This is just to find your final kg. So, as you know, kg will be this divided by this. Okay. So, you will get your final kg. So, this gives you the kg once the weight has been added. So, this will give you a kg. Now, as I said before the previous thing, once the weight is added to the ship, its draft will change. The ship will sink, the draft will change. So, you have to find the final draft. It is very easy. Now, you can do the final draft will be the final displacement divided by length into breadth into rho. Okay. So, this will give you final displacement, we have calculated 17,712 divided by 120 into 8 into 18 into L into B into rho 1.025. In this case, it is 1. Just for information, the density of salt water is 1.025 into 10 cube kilogram per meter cube, and the density of pure water is fresh water is 1 into 10 cube kilogram per meter cube. In all this case, in these problems, in this course, you will write it as 1 ton per meter cube always. Okay. So, that is the density of sea water is 1.025 ton per meter cube. So, that is your density. Then, so this will give you draft is equal to 8.2 meters. This is the final draft. So, draft has increased from 8 meters to 8.2 meters. Okay. Now, you are told that this is a box shaped vessel. So, again we can use this formula, Km is equal to d by 2 plus b square by 12 d. Remember, you have to use for this d 8.2 meters and not 8 meters, because you are finding the Km once the weight has been loaded, provided the weight is now it is just a just to give a problem as such, that there is nothing more to it. So, you have a ship, you have added weight, once the weight is added, now let us find the final Km. So, Km, that means you have to find the final draft. Draft is 8.2 meters here. So, this 8.2 plus this thing, this will give you Km equals 7.393 meters, and Kg is given, where Kg is given, yeah, Kg we just calculated. Kg, it turns out it also comes down to 7.393 meters, which means that Km is equal to Kg. That is what, this is a particular type of problem, means we did a special case, if you remember, where Gm is equal to 0. This is that case, Km has become equal to Kg. By coincidence, Km has become equal to Kg such that Gm equal to 0. So, this once you have now the question is how do you find the angle of deck edge immersion from the data given. Let us see. Okay, now it is a box shaped vessel. You are told that the draft is given. We want this. Remember, we want this phi. Okay. Now, you are told that this is draft is this is final. So, this is 8.2 meters. Then you are told that the depth of the ship is 12 meters. Therefore, this is 12 minus 8.2 3.8. Okay. Now, it is not difficult, right, and this you know this is your b by 2. B by 2 is breadth is given 8 meters. So, this is 9 meters. So, it is now very easy to calculate the deck edge immersion. You can see that tan phi is equal to 3.8 divided by 9, that is all. So, that will give you your angle of deck edge immersion. So, your question is find the dynamical stability up to the angle of deck edge immersion. So, right now you have calculated your deck edge immersion, that is your first thing. Then so your problem is to calculate the dynamic stability, which means that you have to initially formulate your GZ table. So, formulating the GZ table, the only way is using the wall sided formula here, because you are not given the Kn. The only two ways to calculate GZ table is, one, you should be given the GZ table, two, you are given the Kn curve or the Kn table from which you can derive your GZ table, three, from the, if you are given neither of these, from the wall sided formula. Okay. So, we are given neither of these. So, you use the wall sided formula, this is the wall sided formula, this we use. So, we just calculate the so, for we are asked for till, okay, in this case this came to be implies phi equals 22.89. Okay, this is provided you have this, you get your deck edge immersion angle to be 22.89 degrees. So, your problem is now to find your area under the GZ curve from 0 to 22.89. So, you can, I mean, you have to find the area in a step. So, let us see, you can do it as 0, 5, 10, 15, 20 and some other way to calculate from 20 to 22.89 like that. Best thing is to do like the 0 to, no, you, since you are doing wall sided formula, you might ask, you can as well do 22.89, means you put phi equals 22.8. So, you do it like this, GZ as 0, 5, 10, 15, 20 and 22.89. Simple, you can just put it here and you find the area under that. So, GZ we have, so this has one speciality, this problem, that is that you remember that GM 0 became negative in this problem, 0 became 0 in this problem. Okay, GM was 0. So, this is gone. So, it is simplified, it becomes sin phi into this thing half BM 0 tan square phi. So, okay, BM has to be calculated, BM, that BM again same way I by del. Okay, this is a box shaped barge. So, you know how to calculate I, you know how to calculate del. So, I by del, that is what. So, once there are two, again and same thing, if you are not given any information about BM, like you are not given the hydrostatic data, you have to look at the problem, means you must be given that it is a box shaped vessel, or at least that the shape of the vessel is something that you know of, some general shape, but that is not enough to calculate Km. You will be given it is a box shaped vessel, otherwise it becomes too difficult. It will be given that it is a box shaped vessel, then you know how to calculate BM I by del. I is for a rectangle, okay, you know b cube L by 12 and del is the volume of the ship, total volume of the ship, which you can calculate by displacement of the ship divided by the density of sea water. That will give you the, not the total volume of the ship, sorry, it is the volume underwater, volume underwater is the displacement. So, this will give you G z. So, you formulate your G z table, and then it is very. So, here they have calculated same way, yes. So, you make your table like this. So, you have to 0, I will just write one of them. So, like this you have to make the table heel, G z, Simpson's multiplier and function of area. So, like that for 10, 15, 20, might as well do for 22.89. Okay, and you find the area from 0 to 22.89 degrees. 1424 is Simpson's rule, right? Yeah, Simpson's rule. Okay. And once you have the total area, you just have to calculate the dynamical stability as so. Once you have that, dynamical stability becomes your area which you have calculated into your delta, the displacement. Okay, that is in tons. So, you will get your meter square tons that will give you your dynamical stability. Is it meter square? No, meter area is meter radians, right. So, tons meter radians, you will get it like that, that will be your dynamical stability. So, that gives your dynamical stability up to the deck edge immersion. So, here we found out is how to find the deck edge immersion, that is very straightforward, just geometry you can get that. Then next is you have to know for a box shaped barge how to find Km, how to find Bm, two things, because nothing will be given, that formula has to be known, how to calculate the Km and the Bm. So, two things, other than that this, and this of course, there is no difference. The only thing is, in this case you get Gm to be 0, there is no special formula or anything to be applied here. In that formula, for wall sided formula, Gm becomes 0. So, it becomes simplified, problem becomes simplified. Okay. They have one more problem, that I will do. Okay. It says that a vessel has a displacement of 22,500 tons. You are given that the kg is 7.3 meters, km is equal to 7.4 meters, bm is equal to 3.6 meters. So, in this problem it is the second type, you are given the hydrostatic data, you do not have to calculate I, you do not have to calculate Km, nothing, everything is given, Km is given, Kg is. So, you are given the hydrostatic data. Okay. Now, there is a lift which I mean there is a crane which lifts 150 tons of weight from the ship at a so, initially at that center line at a kg of 2.5 meter. So, from this point, from a height of kg of 2.5 meter along the center line, a lift is lifting a weight to a height of kg equals 17.5 meter and 3 meter to the port, I mean what the problem says is that like this, let us say that this is the center line, from here somewhere something from the center line is lifted and it is lifted to the port. Okay. It is lifted from 2.5 meter kg to some 17.5 meter height to the port side 3 meter. So, 3 meter like this to 17.5 meter up there, it was initially at 2.5 meter, that is a problem. Okay. And so, you are asked to find the list because of that, because of this. So, a crane is lifting a small weight from the center line and is shifting it to port, not just to the port, up and to the port like that, that is a problem. So, and you are asked to find the list as a result of this shift of weight. Okay. Now, such a problem, this is the usual method. So, you have the weight kg, moment, then distance from center line, then the moment, this is the moment for the horizontal motion and one is the moment for kg. So, initially you have the weight 22,500 tons and you are told the kg. So, this you can calculate. Now, let us just do this one, means let us forget about the horizontal motion, let us consider the vertical motion alone to calculate the kg alone. What are we doing? You are shifting a weight of, it said, okay, that is given, it is 150 kilogram, 150 tons, yeah, 150 tons. So, if weight of 150 tons is removed from a height of 2.5 meters and it is put at a height of 17.5 meters. So, there is a minus 150 tons at 2.5 meters and there is a plus 150 tons at a height of 17.5 meters. This is straightforward, 2625. So, this gives you the net moment 166500 and this gives you the net weight. So, from this you can get the net kg, that is equal to moment by weight, net moment divided by the total weight, which gives you 166500 divided by 22500, that will give you 7.4. Okay, this is the first thing. Now, if you see the problem, you are given the km also. Right now, you calculated kg, you are given the km as well. You will see that km is also given to be 7.4, same problem, means you are having gm equal to 0. Okay, it is a 0 gm problem. Now, okay, now to do this we need one more thing. This is first part, then you have to do this as well, that is you have to find how much it is moving the horizontal moment. This is to find the shift g0 g1, that is the shift in the g0 in the horizontal direction because of the shift of the weight in this direction. So, from the center line, it is initially at the center line at 0 x, it is at the 0 and then it is moved to port some distance 3 meter, and as a result of this you know that the center of gravity of the ship, the whole ship itself will shift a little to the left side, to the port side it will shift. So, let us see how much that will shift, that is also straightforward only. Initially the weight is at the center line. So, its distance from center line is 0, moment here is 0 and then it is put at a new point 3 meters to the port. So, and so this becomes 450. So, this is this. Now, your g0 g1 is your shift in the center of gravity of the whole ship as a result of the shift in the small weight inside the ship. Okay. So, that is g0 g1 is equal to the moment divided by weight of the whole ship, that will be 450 divided by 22,500, that gives you 0.02 meters. Okay. So, this will give you the this is the G0 G1 or the shift in the center of gravity of the ship as a result of this shift of weight. Now, if you just look back, there is a formula we have done when the particular case, that is a weight has been shifted from one side to another side and Gm is 0, we derived an expression for tan of phi or tan of that angle list. It was given like this, cube root of, I mean there is no need to derive it as such, but it becomes like this. So, we have derived this expression. Of course, it is for the exam. Let us see if something like this comes. I doubt if you can derive it as such. Yeah, it's of course you can, if you can derive it, it's okay, but you will have to remember some things. You have to remember in this particular, in this particular section there are two types. For instance, one, when you have an angle of lol, there is a set of formulas that you have better remember it, I think, and another is when Gm 0, Gm equal to 0, then also you have a set of formulas. It's so that is to be remembered. These are the special cases that I said, because even in the problems, even in the exam, I had to tell you, not you, I mean, a lot of people kept asking me, how do you find the Km, or because many people ask me that. So, that means you are not reading that problem. It said that it is a box shaped barge, that means that formula has, but for this exam I told you everything. So, these are one of those type of problems where you have to remember that it is a special case where we have derived formulas for it, like for the box shaped barge, like that. So, this will give you the tan of list. Now, here you have calculated G0 G1 and Bm, yes, hydrostatic data is given, Bm is given, Bm is equal to Km minus Kb, that will give you Bm. Okay. So, this will give you, list equal to 12.57 degrees to port, because of course, the weight is shifted to port. So, it will list only to the port. So, that is that problem. Okay. So, this is one section is over. Now, we have okay. Now, we have already, I have already told you, there are, we talk about two types of weights in general in a ship. They are lightweight and dead weight. Okay. Of course, there is something called hull weight also before that. Since I am saying it, I will tell everything. First, we talk about hull weight. Hull weight in general means just the hull, okay, nothing else but the hull. You take the ship, you have the hull, there is nothing inside the ship as such except for those structures, except for the walls, like it is the empty building, like that. So, just the hull, that is known as a hull weight of that. It is mainly the weight of steel which is going to make the ship. Now, once you add propellers and some appendages to it, you have rudder, propeller, all those things you add to it. Once you add that, you get some more weight, that is known as the light weight. It still does not have the lot of contents of the ship. I will tell you, the next thing is called as the dead weight. What happens is everything else is added, means the cargo, the ballast, the fuel, fresh water, personnel, machinery, everything. So, all those things are added to the ship and you get the dead weight of the ship. It is not the sum total, what is added is called the dead weight. Light weight is hull weight plus propeller, dead weight is not the sum of all this, dead weight is just the additional thing, all the cargo, fuel, fresh water, the sum of all those is called hull weight, dead weight. So, the total weight of the ship, we usually say it is light weight plus dead weight is the total weight of the ship. Okay. So, light weight plus dead weight, this is the total weight of the ship. Now, we can talk about different types of moments as well. We have talked about moments about the keel, we have done that many times to find kg. If you remember, even in the last problem we did, we were finding the net kg once a weight is added. Initially the ship is there, you add some cargo, you find the final kg. For that we are doing some moment, one moment is coming, like the weight into that kg, that moment is that moment. So, we call it as two things. One, if it is for the light ship itself, it is called a light ship moment, and if it is for that weight in it, it is called a dead weight moment. Okay. Or so, it becomes light ship moment or the light weight moment. These are all moments associated with kg, means something into kg of that. For example, if it is the light weight of the ship, whatever is there, for example, if it is a wall, a bulkhead, what you call, weight of that into kg of that, that will give you one moment associated with it. That moment is called light weight moment. And if it is a dead weight, means if it is, let us say, a cargo, a weight that I am putting there or taking out, it is called a dead weight moment. Now, therefore, we define usually kg to be the total moment or the total moment about the keel, because it is kg divided by the total displacement. Total moment about the keel divided by displacement. This is your kg, and you usually write it in this format. You say that kg is light weight moment plus dead weight moment divided by displacement. Now, also you know that in general, when you increase kg, g will go up, means g and m will come closer together, and gm should be kg is increased, will it become more or less stable? Less stable, right? Yeah. So, it will become less stable. So, as you keep increasing, gm will become smaller. Yeah. So, it will become less stable. Yes. So, if you keep increasing your kg, your ship will become less and less stable. Okay. So, and note that here the light weight moment is the moment of the light ship itself, that is not, that cannot be changed, the ship is already made, you cannot do anything. So, your idea should be to reduce your dead weight moment, so as to increase the stability of the ship. So, therefore, you end up drawing something like this. I mean, we have to have some kind of criterion when we say that this is about dead weight moment. You say that you can increase the dead weight moment to some value, and you increase it beyond that value, the ship starts becoming unstable, or maybe it is not unstable, but it is dangerous, it is in the dangerous zone. Okay. So, like this, you usually you will see a drawing like this. This is displacement. And when that means your kg should be low. Okay. So, you will see a margin line drawn like this, and all those kgs less than this value are okay, these are adequate, this is dangerous or deficient. So, you might see a graph like this in some when in the initial design stages, when you have to say that the ship is, when you are checking whether the ship is stable or unstable, you will see such graphs which say adequate or deficient. So, all those kgs which are below are safe, beyond that line it is dangerous. Okay. So, this graph might not be drawn with respect to kg, it can be drawn with respect to gm, but it becomes slightly different. Gm should be as large as possible. So, so, this same figure, it is actually the same figure kg, it is a, what we have done is that we have changed that kg to k minus kg. So, we just changed it to gm. So, obviously, the figure will shift, the region which was adequate will become deficient like that, because gm has to be as high as possible. So, this region is adequate and this region is deficient. Okay. So, these are two curves that you might see in your design, means you will be told that you should have a stage when you should be in this region. So, you should always be in this region, and so you calculate and you say that this is either in a stable region or an unstable region like that. Then this problem is just an application of this. I will just tell you what this is. It just say this problem, that is, it says that there is a vessel which discharges 15,000 tons. So, that means the displacement of the vessel is 15,000 tons, and you are told that some loading is done on it. For instance, there is a in the cargo number, hold number 1 4,000 tons, you are given the kg, hold number 2 3,000 tons, you are given the kg equals 6.5, like that you are given different values. And then the problem is you have to check with a chart, means I just drew here this, there is a chart like this. Okay. You have to look at this chart and say whether the ship is stable or not. So, what you need to do is, in such a problem, I will just write this thing, let us say this compartment, then weight, then kg, you have the moment, and so what you have here, what you do here is, this moment is actually giving your dead weight moment. So, for each compartment 1, you are given what is the weight there, you are given the kg. So, what you should do is multiply the 2 and get the moment, you sum up all the compartments, okay, all the compartments you sum up, you get the total dead weight moment. In fact, here there is a chart given like this, which says that displacement versus dead weight moment. So, as you can see here, as the dead weight moment increases in the right side, as you go along the right side, dead weight moment keeps increasing. As the dead weight moment keeps increasing, kg keeps increasing. As kg keeps increasing, the ship becomes less and less stable. Okay. So, after this particular line, this curve, the kg becomes the dead weight moment, the ship becomes exactly deficient, the ship becomes deficient. So, what you have to do is, in this problem you look at all the total dead weight moment and you look at the displacement of the ship, read where is it lying, is it here, is it here, is it on the line, then you say whether the ship is deficient or not. I mean, you are not going to face any such kind of problems, because that means such charts have to be given, that long big charts, that I do not think we will do that. And you might end with something like this. Okay, you will see a line like this, which says that it says that summer load displacement, which means that you usually cannot go above this. Okay. That means there is always a limit on every ship, that is the water line of every ship, the draft of every ship cannot be increased infinitely, means there has to be a fixed amount of freeboard always, that is all fixed. There is a range, but there is a limit, you cannot go beyond that limit. So, this is that limit, summer load displacement is that limit. Therefore, your ship, you cannot increase your dead weight moment such that limit is exceeded, that is not possible. So, you cannot have beyond this line, this horizontal line you cannot have beyond that region beyond is not allowed. So, if you have to say that your ship is, for that particular condition the ship is okay, it has to be somewhere here, okay, you have to get it here, anywhere else it is going to be a problem. Okay. Then okay, one small thing I will just complete and stop. That is okay, it is nothing much, it is just that so, you are having displacement versus dead weight moment. We are just looking at, so here you will have a line like this, which is called as summer load displacement or load displacement, something like that, cannot cross that. So, usually you will have a position where you are at, let us call this C0, the ship is initially here. Now, there are different directions in which it can go, that is, one of the directions is, means what we are doing is some weight is added to the ship. Note that whenever some weight is added to the ship, its dead weight moment will only increase. Okay. So, it will go to the right, this line, if you draw a line from here to the final state, it will go to the right only. So, somewhere it can go here, this is one possible C2. So, if you have this curve like this, you can, this is the limiting curve. So, beyond this it is inadequate, here it is adequate. So, this condition is okay. So, we can say that this C2 is a stable state, that is one possibility. Then it can go here sometimes, if you keep increasing the dead weight moment, it can go to some state C4, which is an unstable state. So, here it is not adequate, it is deficient. Then what is this? This is now another possibility is you can change the dead weight moment without changing the whole displacement of the ship itself, means from one you are moving to another, exactly. So, the displacement of the ship is not changed, but you are moving one weight from one point to another point, as a result the moment has changed. So, you can move like that, it will go like this horizontally, okay. Displacement will not change, it will go in this fashion, and after a particular value it will cross it and it become unstable, till then it is okay. So, these are different stages, and just to complete that, you will have, in case you are removing a weight or you are taking away a weight, it will go down, okay. In this curve it will just come down. So, your dead weight moment is decreasing, it will come down like this, and means displacement will also decrease because you are removing a weight. So, it will come down, and similarly you can change your dead weight moment like this also, without, this will become more stable, without changing the displacement you are changing the dead weight moment, ship becomes more stable. So, these are different possibilities. Okay, I think I will stop here. Okay, thank you.